So now we are going to discuss about some optimization technique. Okay. So we have discussed some what is loss in logistic regression. We have discussed, right? So loss means the error. Okay. If you have a data points, so the perfect fit line in linear regression, it should be like this. Okay. So this one is X, this one is Y. So this one is a perfect fit line. So what is the error here? The difference between this point, this point. This is called the residual error. Okay. So the sum of residual error y minus y prediction whole square divided by n. Okay. This is mean square error. So this is the loss here. Okay. So our aim is for optimize that algorithm. We have to minimize. We have to reduce that error. Okay. So reduce as much as possible. We have to reduce. So instead of this fit line, if the automatically in the algorithm what it does, so it moves so slightly and calculate the error, and then move slightly, then adjust slightly. Okay, and the line perfect fit line is moves slightly up or down, then calculate the loss. So it will finalize which one gives very less loss or zero loss. It detect. Okay, that is the best line. It works like this algorithm, all the algorithm. Okay, even this one is easily interpretable. That's why I'm showing this. But if you take a logistic regression, so everything is works like this. Okay, every algorithm has some loss function. Okay, so loss. So in logistic regression, there is a we have seen some log loss. Okay, loss function. So everything. So entire if loss means we have to reduce. Okay, loss means we have to reduce through various techniques. How to reduce? What we have, we can do some regularization techniques. So we can apply L1 and L2, or so we have to do some hyperparameter tuning. So internally, the optimization technique. So if there is any hyperparameter tuning, right? If you change anything, the optimization technique also internally it will change. Okay. So we will see what is optimization technique. So our optimization technique, main important of optimization is, so we have to find the best algorithm, best model, okay, through reducing the error. Okay, for that we have to know a little bit about some differential calculus. Okay, so differential calculus. So we'll see. Okay, simple. Already we would have studied in our schooling, but I will just explain in a simple way. Okay, there are two differential type calculus. Okay, one is differentiation. Okay, already we dy by dx we have studied this formula, right? Next is some integration. So like we have seen like this, right? The integration. So if you have a formula y is equal to f of x, in our entire machine learning, we create some equation, right? So if you integrate this one dy with respect to dx, so it means df of dx. It means what? Okay, you have some equation. Okay, some here dy by dx means, so you have, if you have a graph like this, okay, something, you have some graph like this. This one is x1, this one is x2. For this x1, this one is y1, this one is y2. So you are applying some x value here, you can get y. So in the entire equation, create this kind of graph. Okay. So what dy by dx, what it says. So how much y change it, y changed, okay, as our x change. Okay, so if x1, it the initial value from x1 to x2, it will be moving here. At the time, y also getting changed. So what is the rate of change with respect to x? What is the rate of change for y? Y with respect to x changes. Okay, so that is differentiation. So entire, okay, deep machine learning. So we are using the every algorithm used for differentiation for finding the best model, the optimization. So differentiation is mainly used for that optimization technique. So in deep learning, extensively it is getting used. Okay, so we'll see one by one. Okay, this one is here. This one is x2. This one is x1. Okay, how to calculate the rate of and the change? Okay, so here, if x2 moves here, x2's value is high. So we want to reduce y value. Okay, so in this scenario, what happened? We can adjust the x. Okay, move to x2, move to x1. At the time, so we can calculate what is the value of uh, y. Okay, y is this value here. So if x is from x2 to x1, it is getting changed. What is the rate of change? So for that we can use some slope. We can draw some line. Okay, so this line. So we can find the slope of this line. Okay, slope of this line. It means the tangent of this line. Tangent of this line. Tangent of f of x. Okay, this is a y is equal to f of x. So tangent of at this point. So if you so tangent tan theta is equal, okay, first dy by dx is equal dy by dx. So we can use some this, right, some gradient, some so equivalent to this one. Okay, x. So limit, what is the limit? X moves to 0. This one is a 0 position. Okay, if it is a 0, it moves to 0. X limit to 0. Okay, so through that we can calculate. So so every position, if x2 moving from here to here, from here to here, in this position we have to calculate what is the rate of change. Okay, dy by dx. So like this it works. To theta so we can calculate this is the rate of change of y from this position to this position, and this is the rate of change for x. So tan theta is equal to dy by dx. So through theta also we can calculate the tangent. Okay, so here this one is some curve. Okay, okay, I will explain. Okay, yeah, this article. So very important topic. What is for optimization technique? So we are using gradient descent. Okay, gradient descent. Okay, so for linear equation, we know that, right? y is equal to mx plus c. Okay. So there is a two parameter. This one is a x, this one is a y. It creates a relationship between the data point. Y is equal to, it identifies what is the best fit line. How to identify? We know x and y. If you adjust the m and c, so we can identify right y. Okay. So y already know. Okay. X and y already given values. Okay. Only thing is we have to find m and c. Okay. Through optimization, we have to find best m and c. How to find best m and c? Which m and c gives low loss. That is the best m and c, right? Okay. Here through tangent. Okay. Tan theta with the m is equal tan theta. That is a slope of the line. So this one is a dependent variable. Okay. Market spending, marketing spend, sell lakhs. So sales in crores. So we have two data. Okay. So two data, one is X, input feed, another one is output level. So here, if you draw this one, so we have to find best fit line for this term. That is a linear regression. Am I right? So here, so the line, okay, we have found three different lines. Okay. So three lines, each line gives different loss. Okay. A different residual error. Okay. If you sum up, if you find the MSE mean square error, so you can find, so three lines error. Which one gives the lowest error? That is a best fit line. Okay. Okay, we have to measure value like this for every line. Okay, this is the error. This is the actual data point. This is the best fit line data points. So the difference is, so y minus y prediction whole square. So this one is, we are squaring that difference. Through that we can calculate the error. So this one is a predicted value. So always the predicted values comes on the line. Okay. Okay. So there is a all algorithm, there is a cost function. What is cost function? As I said earlier, the loss is a cost function. Okay. So loss, mean square error. Okay. So we know that this one is a mean square error. Okay. So mean square error is y prediction. Y prediction. So we know, right? Mx plus c. Okay. Mx plus c is the y prediction. This is a formula. So f of x. Okay. So if we apply that one, so we can find the mean square error. After building model, we are getting mx plus c. So if you pass, if you know yi and this one is a y cap. So if you find the difference, you can find the mean square error. So what is gradient descent algorithm? Okay. For that, here what we have to do for minimizing the loss in the cost function. One is cost function. Okay. So the cost function nothing but differentiate. Okay. Difference d of m error divided by with respect to. So what is here? This one is the entire equation is f of x. Okay. So here we have two values, m and s, m and c. Okay. So we have to find optimized value m and c through optimization function. Okay. We have to adjust m and c and find the cost function, which m and c gives lowest values. We have two variables, m and c. So with respect to differentiate, okay, msc cost function d of msc divided by dm. So this is a one differentiation. Another differentiation is d of msc with respect to c dc. Okay, we have to find two differentiation function. So through msc, okay, with respect to m and c. Okay, this is a. So for various m, this one is a 3D diagram. Okay, this one axis is error. MSC error function. Okay, cost function. Another axis is C. This axis is M. Okay. So if you remember our application, what formula we are using? U is equal W0 plus W1 X1. Okay. If it is a single variable. Okay. This one is W0. This one is a W0. This axis is a W0. This one is a W1. Okay. So weight. Okay. As a machine learned term. So we can call it as a weights. So if you adjust the weights, okay, through that you can minimize the error. Okay, a loss for cost function or loss. Okay, so we have with respect to m value. So there are two variables, right? M and C. With respect to M, we are integrating. So partial, this one is a partial integration. We are integrating. There is more than one variable. That's why we are doing partial integration. So partial integration. So entire cost function. So what is the cost function here? Cost function. So we know already we know that, right? Cost function. This is a cost function. So we are integrating this cost function. So we are doing some partial integration because we have two variables M and C. So with respect to M, we are integrating that cost function. So if you apply integration for this, okay, so you can get 1 by n as a constant comes outside of the function. And then if you apply, normally we know, right, y is equal to x squared means dy by dx is equal to 2x. Okay. Y is equal to x means dy by dx. What is it? Dy dx 1. Okay. So here, if it is a y is equal x n means dy by dx, what is dy by dx n x n minus 1. Okay, do you remember? And we have studied these things. Okay. Okay, like this, if you apply this one is a square. So if you apply the same logic here, you are getting finally this formula minus. Okay, this one is a minus value. That's why minus 2 of divided by n. So xi. So comes this one. You can get this one. Final. Okay. So this is the final for with respect to partial integration of some cost function divided by respect to m. Similarly, we can calculate the cost function with respect to C. The same way we can calculate. Okay, here we are using m max I, right? So that's why x is what is the okay? Suppose 2x. 2x means y is equal to x. What is the dy by dx? So 2, right? So here C. So with respect to C, we are integrating. So we are getting this finally. Okay. So the integration. Okay. Okay. So finally, okay, I will take only one variable. Okay. There are two variables M and C. I am taking only one weight. Weight is here. Okay. This is the loss function. Loss or cost function. Okay. Cost function. Integrate loss function or cost function. Okay. Loss with respect to W. Okay. Weight. I have only one weight. In that example, there are two weight. Okay. First, it will fix some weight. W0. Okay. W0. And find the loss. So loss is here. Okay. Then change the W to the W1. Okay. This is W0. So W0 losses with W0. Okay. So then W1. So W1 plus is WL with respect to W1, right? This is W2 loss. So now loss is getting reduced. Okay. So how to identify W1? W1, so there is some loss, right? W first is initial, so randomly getting applied some weight. Then W0, so minus with respect to change, how much the loss getting changed. Okay. Through that it calculates W1, this position. Okay, from here to here. So here, okay, now think some constant one, but some minute value is getting applied. That is called learning rate. Through learning rate, so it will if you put high learning rate, what happened? The W1 instead of here, so it suddenly move here. If it is a slow learning rate, it moves the next position, next position. So every places it calculate the slope. Okay, if slope is 0 or very low value, so here also slope is getting calculated. Here slope is some high values. Okay, slope theta is high, but if you see here slope tan theta is 0. Okay, here 0, here tan theta is huge. Okay, here how about here tan theta, it has some theta, right? So only here only it has tan theta is 0, the tangent of this slope is 0. So here only the loss is here, the entire graph in this position, in this place only it has a minimal loss. So so it finds the weight of this position. Okay, then what is the weight of this position? So it's a final weight. Okay, through this is called gradient descent. So first it selects some random weight, adjust the weight. Okay, through that it compare with the previous weight. Okay, previous weight and loss. So if when it will be getting stopped, if you adjust here, even though chances are there, right, it moves further, right? So it should stop here. How to check? Okay, it checks with the previous weight every time. Okay, here I am showing only W1, W2. Again, W2 come here. Next weight here, W2. So it checks, compare the weight with the previous weight minus learning rate of tau L divided by tau W1. Okay, partial derivative. Through that it identify. If both the values are same, it doesn't have any loss, right? So that's why our minimal loss. Okay, through that it identified. Okay, we move the final position, so it stop. Okay, the optimization algorithm stop with this final weight. Okay, this is a gradient descent. Okay, so we can call it as a simple. Okay, one guy. Okay, here if you roll any that ball right here, if you think this is a bowl, okay, so rice bowl. So if you roll any ball here, any marble ball, so what happens? It slowly moves here and here and here. Finally, so it reaches this final position. Okay, the minimal position. So this is called minima. Okay, so the loss is minimal in this point. That's why it's called minima. Suppose in other graph, if you have this kind of graph, okay, so if you apply some any, this one is W, this one is loss function. Okay, rho L divided by rho W. So here we are having so many loss, this minima values. Okay, this one is a local minima, this one is a local minima. So local minima. So for adjusting weight, we suppose sometimes the problem it's stuck here. Okay, with but actual minima is global minima is here. Okay, through adjusting the learning rate, so we can find the global minima. This is a global minima. This is a local minima, wherever we are getting some local minimal value, right? So we have to adjust. Suppose if you adjust the learning rate, chances are there coming here. Okay, like this we can find the position. Okay, learning rate. So like this, there is a maxima. Okay, this is a global maxima. Global maxima. These values. This is local maxima, the maximum value. Okay, last is a maximum here. Global, sorry, global maxima. So whatever the point in the entire diagram with the last function, so the lowest dip of is called global minima. Highest peak is called global maxima. In between there is a local minima, local maxima. So okay, as I said earlier, now update the current value of M and C. And so this one is a weight 1, weight 0. Okay, so sorry. Okay, you can give this. So M1. So in this diagram, so this one is a M, first M, and it predicts the next M here. Okay, with learning rate. So derivative. Okay, with respect to M, the last function here. So minus would be previous M. Okay. If suppose there is no loss, means M and M0 and M1 both are same, right? At that time it will stop. Okay. Because in this position, so here the previous some M previous values are there, right? Suppose M9. Okay. Next is M10. So here M10, M9. Okay. So if loss is very low, so what happened? M10, M9 both are same. This equation satisfied. So that time it will stop. Okay, with this best M value. Similarly, C. Okay. This is a gradient descent. Okay. Okay. Go through the definition. Okay, what is gradient descent? Opinion. Finding a local minimum of a differentiable function. Okay. Okay, if you see that the diagram in the top view, right? So it so move like this. Okay, move towards the minimal point. Okay, here what we have discussed for logistic linear regression. Okay, this one is a linear regression. Here the same formula. So this one is new weight. So here weight is put at some theta. Okay, here old weight, new weight, old weight minus alpha. This one is a learning rate, 1 divided by M and the error equation. Okay, so yeah, error function. So this one is a f of x divided by a minus the difference f of x. This one is has 0 x means f of x. Okay, the final y is equal to mx plus c minus actual y. So we are finding the difference. Okay, so after applying the differentiation, if this one is entire learning rate, this entire formula is okay. What is the L divided by M with respect to M? Okay, we are applying some learning rate. Okay, or here theta, theta here weight is the theta, tau L divided by tau theta. So H0 of x. This is our equation. Okay. So here, what is the equation? Already what we have seen, mx plus c, only scalar value. If you have a vector, so the transpose of vector, w vector, okay, this is the weight vector, theta t is a wt x plus w0. If it is a 0, we can put. Here, there is no w0. So this one is the equation, our linear, so regression equation, okay. The line passes through origin. That's why w0 is 0, okay. So here the equation minus actual value. So we are finding that error. Then that is a MSE cost function. So we are integrating that cost function and adjust with the weight. We are finding new weight. If both the weights are equal, the gradient descent algorithm stops its optimization. Okay. So this one is a linear regression. What about logistic regression? Here h of x. Okay. If you remember, our equation is like this, okay? Sigmoid function, am I right? Sigmoid function. So we have to calculate the last one, the same formula. So here f of x mx plus c, okay? Wt xi. But here, so it is a sigmoid function. So that's why a linear or logistic regression, the main properties, it follows the sigmoid function curve, okay? Logistic regression curves should be like this. So it the repeat the same thing here, okay, but loss function is here the same loss function, but the equation is h of x, f of x is different. Here f of x different. That's it. Okay. Okay. This is okay. Some between two variables. Okay, depends on attack. Pokemon data set. Okay, this first random plane, it looks like this. Here, okay. So this is a plane, okay. So this is sorry, best fit line, okay, initial line. So error rate is MSE is high, okay. So we are adjusting the slope, okay. Slope is 0.4 here, okay. Then slope is 0.45, 0.5. Okay, here. So this is error is very low here, okay. The slope value is high, okay. I said okay, slope is 0, but here the slope is okay, this slope, okay, we are doing this slope, but here if you draw slope here, right? So this slope means here they are referring this slope. This one is how it is getting calculated, okay? The slope, okay, here the tangent value is 0 here, tan theta. So if you adjust this one further, so again you can compare, okay, the best fit lines moves away, okay. So which is the right plane, okay, here. Okay. So here we are having some scatter plot and the line, okay. Here we are comparing with the mean square error. So with MSE and that point, okay. So weight, adjusting the weight. So if you adjust the weight, this one is a weight, okay. So if you adjust the weight, so your line is getting changed, okay. So this is, I will show you one more. So everything what we have discussed earlier, explaining here. So we don't need to do any calculation internally. Okay, it find the best hyperparameter. So only thing is we have to add some regularization and what is that, hyperparameter tuning. Okay, so machine yeah, algorithms handle that gradient descent, okay. You have, but in deep learning you have to specify which optimization technique you have to use, okay. There is a stochastic gradient descent, adam and rms pros, various optimization techniques are there, okay. Here, this one is w new, finding the new weight compare with the old weight. Okay, this is called the gradient. Okay, so whatever we are integrating the function, okay, that is called gradient. So function weight, this is the last function, integrating derivative differentiation of that last function is a gradient. Okay, here, okay, we are passing, okay, x and y. So between x and y, so weight start with, weight is only one value, 0.5, and alpha learning rate is different, okay. Initially draw with this weight 0.5, this is a weight 0.4, 0.5, right? So then we are using alpha values 0.000, how many 0, 401, right? So learning rate is very slow. We'll see how it. If you move, if you adjust the for this learning rate, so it moves slowly. Next point, okay. So every time it's calculate the loss, compare the weight and loss. Okay, slowly it moves. After that, it won't move because in this position, the new weight, old weight, both are same. It means there is no loss. That's why it stops here. Okay. So now we are getting best fit line. So slope is 0.9. Okay. Now just change some alpha values like 0.00 instead of 0.00001. We are changing to 5. Okay, learning rate. We increase some small amount learning rate. Okay. Here, if you see a point weight is 0.5. If you increase the learning rate, what happens? You see the difference, right? So the previous example, this one. So learning rate is playing major role here. Okay. Increase learning rate. So we will just increase further more. Okay. So instead of 0.0005, here we are using 1.5 for same weight. It's already okay. Here, see, if you give high learning rate, it goes here. So the learning rate is hyperparameter. Through that only you have to, because sometime what happen, your algorithm starts in the local minima. Suppose in this graph, this is a global minima. Here you are creating, adjusting some weight here. So if it is a small weight, a small learning rate, what happen? It's stuck here. So you have to give some high learning rate. This is a hyperparameter. We have to try with the various values. Through that, which one gives the lowest MSE? So we can find get the that hyper learning rate. So if you adjust this, yeah, you can see, right? So with the high learning rate, it moves from it. How about learning rate instead of 1.5? So if you give 1.8, what happens? See, so it moves vanishing gradient descent. Okay, this one is so vanished. So the point is getting vanished. So here, if you get this kind of if you give high learning rate, what happen? It move away from the your last function. Okay, at the time, how is the your fit line? Okay, it is here. Okay, entirely wrong model, right? So you think, okay, we are giving best learning rate, best hyperparameter. We are not sure. Okay, only thing is, so we have to adjust with various values through hyperparameter tuning. So this one is what we have seen here is only one parameters. If you see with the two parameters, this is a MSE, this is a weight 1 and weight 0, two weights. So it should be like this. Okay, in this diagram, we have to find the minimal lowest point, lowest error. So we have to find, we have to use two variables here. Yeah, it should be like this with two parameters. Like a bowl, okay, a rice bowl. So it reached the lowest point at the place. What is that? W0, W1. That is the best weight vectors. Okay, it's the same thing. We can use it for logistic regression. So logistic regression. So this is a okay. So logistic regression, sigmoid functions. Sorry. So fit line, okay. So ultimate, yeah, aim is, so we have to reduce loss function through adjusting the weights, okay. So gradient descent is working well with that scenario, okay. There are some other type of gradient descent. One is stochastic gradient descent. Already we hear that word, right? Gradient descent. SGD, stochastic gradient descent. So in the normal gradient descent, we are taking entire training data set and build this model and finding the best, okay, local minima through adjusting the weight, okay, through differential calculation of loss function, differentiation of loss function. Stochastic gradient reader means, so it takes every observation and find the last observation. So one by one, okay, we are using each and every point individually and find the best hyperparameter, okay. So through that, we optimize the entire data point one by one, calculate, apply the gradient descent, okay. Instead of entire data point, we are using each and every point, okay. Through that, we identify the best, okay, best weight vectors. That is called stochastic gradient descent. Another one is mini batch gradient descent. Mini batch gradient descent. So here the mini batch means entire training data. Sorry, T drive here individually all the points. Sorry, excuse me. So here the D train is getting splitted into small batches. Okay, D1, D2, D3, D4, like this. So it calculates, instead of single points, it calculates small batch size. So the algorithm is gradient descent itself. Only the source data here, individual point, is a batch of points, bunch of points. Okay, that is a mini batch gradient descent. So algorithm, everything same, concept is same. Our ultimate aim also same. Okay. So only thing is we have to find a best W vector through loss function. Okay. So go through this article and find the definition of search some article, find the definition of gradient descent and stochastic gradient descent and mini batch gradient descent. Okay, so Priya, yeah. So go through the article and write the definition and share it. Okay.